This is the playlist about reservations in two-way slabs by means of yield lines. And in this video, we will deal with case 3 type of reservations. Suppose that we have a rectangular slab with which is a two-way slab. That means that B, the dimension B, this one, must be between A and 2A. We have drawn the yield lines of the slab without a hole, and now we will consider case 3 hole, which are rectangular holes not cutting any yield line. So it's just a rectangular hole coming from there to there. So the conditions are square hole, that means D1 and D2 are equal. At the edge, that means that here at the edge that D4 is 0. And between those two yield lines means this condition has to be fulfilled, and it holds that D1 must be smaller than A over 3. These are the conditions. Now we will show you visually what it means. It's a square hole starting from the top, going down, down, and until the bottom, and it's not cutting yield lines. Now, for this type of hole, we do the calculations of the work done by the external forces. Again, we will use the superposition of load cases. So we will take up we will consider the slab without the hole and subtract the effects of the hole. So the green colored area is triangular elements, and the orange one, the rectangular. So we know that for the triangle elements, the mean deflection is delta over 3. So this is this one. So this area is A over 2 times A over 2 times A times 1/3, and we take it twice, 2 times. And for the rectangular, it's A over 2, and it's in fact B minus A, which is those two areas. And when we got this, we subtract the whole. But now we know that the whole, the deflection is here delta. So at the distance D1, the deflection is delta X, and it means this is this deflection. So we have D1 times D1, and then with this the deflection. E over Q delta is then equal to this formula, and the work done by the internal bending moments, D over M delta, is then equal to, because none of those yield lines are cut, so it's like there is no hole. So it means you have this yield line projected to the south, which gives you B times the rotation, which is delta over R over 2, twice, because this can also be projected to the north. And then the same happens for the left-hand side and the right-hand side, which is this. So that gives you, when E is equal to D, M is then equal to this formula. First of all, we notice something peculiar here. That is that this bending moment is independent of D3. So at first sight, you think something is wrong. D3 is this dimension. It's the position of the reservation in the slab. How can that be? In second thoughts, this is correct. Why? Because we are not cutting any yield line. So because you are not cutting any yield line, the bending moment here is independent of the position of the hole. We give you an example, example 1, a square slab. Depth of the slab is 200 millimeter, the concrete cover 25, the floor finish is 2 kilonewton per square meter, and a mobile load of 10 kilonewton per square meter. Now, What is the needed reinforcement in this slab? We look at the load in ULS, ultimate limit state, and this is the permanent loads times 1.35 plus the mobile loads times 1.5. It gives you 24.45 kilonewton per square meter. We have this as a parameter. We use the formula of the previous slide, this one, and we have 25 kilonewton meter per meter. The lever arm in X direction, it's the total depth of the slab minus the cover minus point of gravity of the reinforcement. We assume one layer of reinforcement, and we assume, because of this value, we assume a diameter 12. If this is not right, then we redo the calculation. So the lever arm in X direction is 164. In Y direction, which is the second layer of reinforcement, and you know the reinforcement in X and Y is the same, so it's 152 millimeters. And the mean lever arm is then 158 millimeters. The needed reinforcement is then given by this formula, and we have 442 square millimeters per meter. This means a diameter 12 every 250 millimeters, or 4 diameters per meter, for rebars per meter, gives you 452, so which covers the needed reinforcement. A second example is an existing slab reinforced in two directions, and they want to make a reservation of 1.6 times 1.6 like it is indicated here. And the question is this possible? Huh? Can we do that? Now, you don't know the original load that the slab was designed for. So we use the maximum bending moment of the slab without the reinforcement divided by the load, because this is only a function of the geometry of the slab. So we find this is 1.64 meter per meter. And now we look when there is a reservation in the slab. Again, we divide the bending moment by the load, and this is from the previous slides, the formula of the previous slides. We find 1.56. Now it's easy. You just divide this by that, and we see that we have an increase from 1.56. We have an increase in 5% of the bearing capacity. So it means making this hole. We can do that without losing any bearing capacity. But just understand, if you make this hole, all those rebars which are here and in this direction must be anchored sufficiently. Otherwise, you will have to make it's like the hole is bigger, huh? Because when there is the anchorage is not all okay, the steel cannot yield. So we assume in all our exercises that the anchorage is okay. So the bearing capacity is defined as maximum bending moment without the hole divided by the maximum bending moment with the hole. In formula, it will be like that. Then we make the formulas without any dimensions. Then for type 2, no, it must be type 3. For type 3, reservations in the slab. These were the conditions. And you can rewrite the formula now of bearing capacity, this formula, with the dimensionless parameters. Now we can make a graph. On the y-axis is the bearing capacity for different values of alpha, which is the geometry of the slab, and in function of the size of the hole. We know that alpha 1 must be smaller than 1/3 of the smallest size of the slab. Otherwise, you are not in case 3 hole. So that's why this is cut off there. I will concentrate on this. First thing you see is that every graph or line is above 100%. So that means that by making a hole type case 3 does not influence your bearing capacity. Now let's take this interesting point, which is 1/3 of A, and let's take the red curve here to give you just a visual indication. It is a hole like that for the red curve. It's 1.5. It means this is 1.5 times this, and function of alpha 1, and this is alpha 1. Then you will see uh, for this side that whatever you do, the bearing capacity is always 1% more than the original one, notwithstanding that the hole moves from there to there. So it does not influence the bearing capacity. Let's now look at the extreme and the right-hand side of the previous graph. We look at the extreme. We know that this is occurring at alpha 1. The size of the hole equals to 1/3 of the minimum size of the slab. That means that the bearing capacity is for alpha, and then alpha 1 is 1/3, and I call that the maximum bearing capacity of the slab. And you can fill it in the formula, and you arrive at this simple formula. You can make a graph of it. So for alpha, the dimensions of the slab between 1 and 2, between 1 and 2. So the maximum is 112%. And you see that it's always more than 100%. So as a conclusion, a square hole at the edge smaller than 1/3 of the smallest side of a rectangular concrete slab has no loss of a bearing capacity as long as the yield lines are not crossed. So this hole moving from there to there, as long as the yield lines are not crossed, no loss in bearing capacity. So yes, you can make a hole in a slab without any problem. Of course, what we set for this side, it's always the same for the other side. But if you stay within the yield lines, you can make the reservation in the slab. You will not lose bearing capacity.